Welcome to the Applied Psychrometrics webinar featuring Titus Senior Chief Engineer Ken Loudermilk. Before we begin the presentation, please be aware of the following items. You are welcome to submit questions at any time. There will be a Q&A session at the end of the webinar. This webinar will be available in the Titus University section of our website and on our YouTube channel within 7 to 10 days after this broadcast. For our Lunch and Learn attendees, to ensure everyone receives their CE certificate, please email us at communications@titus-hvac.com. CE certificates will be sent out after this webinar series has been completed. You only have to attend one full session to obtain the certificate. Now let's begin the webinar.
Hello, and welcome to our webinar. I'm Ken Loudermilk, Senior Chief Engineer for Titus. Today, we're going to discuss psychrometrics as it relates to HVAC system processes. Psychrometrics is the science of water and air that deals with the properties of moist air mixtures. In this webinar, we will introduce the psychrometric chart as a tool to quantify these properties as they change during common HVAC system processes. Air is one of the elements that sustain life on our planet. The air that we breathe consists of about 21% oxygen, 78% nitrogen, and trace amounts of other gases. An indoor air mixture also contains about 1% moisture when ratioed by its mass. It's important to note that the properties of an air mass are dependent upon its temperature, moisture content, and barometric pressure. First of all, let's identify a few terms that are helpful to know when considering a moist air mixture. Dry bulb temperature is that which is measured by a thermometer freely exposed to an air mixture and shielded from any radiation. The dry bulb temperature is not affected by moisture content and is commonly referred to as the air temperature. Wet bulb temperature is that read by a thermometer whose bulb is covered by a water-soaked cloth over which air is passed. The adiabatic evaporation of water from the cloth transfers heat to the airstream, which renders the cloth's surface temperature lower than the dry bulb temperature of the air passing over it. Sensible heating and cooling processes change a mixture's dry bulb temperature without affecting its moisture content, where, by definition, latent heat transfer processes involve a change to a mixture's moisture content without affecting its dry bulb temperature. Specific volume and density relate the volume occupied by an air mixture to its mass. They are used to convert the volume flow rate of a moving air mixture to a mass flow rate. Finally, sensible heat gain ratio is the ratio of a space's sensible heat gains to its total heat gains, which are sensible plus latent gains. The psychrometric chart is a tool we can use to identify the properties of a moist air mixture. The chart shown is based on standard air density, which is defined as that of air at sea level, or 14.7 psi barometric pressure, and 69-degree dry bulb temperature, 50% relative humidity. Standard air can be plotted on the psychrometric chart as shown. The chart allows you to quantify numerous properties of an air mixture by simply identifying only two of its attributes. All of the physical and thermodynamic properties of a moist air mixture may thus be quantified by the use of a psychrometric chart. Now, let's explore the chart. The x-axis of the chart represents the mixture's dry bulb temperature, which is indexed by the vertical lines within the body of the chart. The y-axis of the chart represents the moisture content of a mixture, expressed as a mass ratio of its water vapor to its dry air. This is referred to as the absolute humidity or humidity ratio, designated by the letter W, and commonly shown in pounds of water per pound of dry air. Humidity ratio can also be expressed in grains of water per pound of dry air. As there are 7,000 grains per pound of water, this results in ratio values without decimal extensions. I find it easier to use, so we'll continue to use grains throughout the rest of this webinar. Finally, the wet bulb temperature is indicated by diagonal lines on the chart as shown. Notice the curve formed by the left end termination of the wet bulb temperature lines. This curve is known as the saturation line. It is established by points where the mixture's dry and wet bulb temperatures are the same. The point at which the dry and wet bulb temperatures are the same is also referred to as the mixture's dew point temperature. The dew point temperature represents the minimum temperature a mix may be cooled to before it starts to condense moisture. For example, a mixture whose dry bulb temperature is 90 degrees and wet bulb temperature is 75 degrees can only be cooled to around 69 degrees before it reaches its dew point temperature. Further cooling will result in condensation and the removal of moisture from the mixture. Note that a change in moisture content also affects the wet bulb and dew point temperatures of the mixture. The pink curves in the body of the chart represent equal values of relative humidity. The relative humidity of a moist air mixture is defined as its moisture content expressed as a percentage of that of a saturated air mixture at the same dry bulb temperature. Notice that the 100% relative humidity curve coincides with the saturation line. The relative humidity of the mixture changes upon a change in the mixture's dry bulb temperature, even though its humidity ratio or absolute moisture content may not change. This is because the mixture's moisture retention capacity to retain water increases with its dry bulb temperature. Undoubtedly, you've heard people complain about how uncomfortable it is outside referencing the relative humidity level. There's a big difference between a relative humidity of 60% in Seattle, where the dry bulb temperature may only be 60 degrees, versus that in Houston, where the outdoor dry bulb temperature might be 90 degrees. Although it's often referenced, relative humidity doesn't really mean much in terms of most HVAC calculations. The psychrometric chart can also quantify the enthalpy of an air mixture. Enthalpy is the total heat energy of the mixture expressed in BTU per pound mass. It is affected by changes in the mixture's dry bulb temperature and/or moisture content. Any change in either results in a corresponding change in the mixture's enthalpy. Finally, the specific volume of a mixture expresses the volume in cubic feet that 1 pound mass occupies when at sea level barometric pressure. A mixture's density is the inverse of its specific volume. For example, a mixture whose specific volume is 13.5 cubic feet per pound mass would have a density of 0.074 pounds mass per cubic foot. When a mixture's dry bulb temperature is increased, it expands and thus its specific volume increases while its density is reduced. Also note that the specific volume, enthalpy, and humidity ratio all reference the mass of dry air within the mixture. Thus, the specific volume and/or density of a mixture must be determined to convert between the volume flow rate and the mass flow rate in energy calculations. HVAC systems are designed to provide a comfortable and healthy environment for the occupants of the spaces they serve. In order to do so, they are designed to maintain space temperature and humidity levels and are thus tasked with compensating for any heat or moisture transfer that are related to processes and activities within the space. Space-sensible heat gains may originate from a number of sources. A significant percentage of the heat generated by space lighting is absorbed by air movement and distributed throughout the space. Heat generated by equipment within the space also contributes to the space-sensible heat gains. External walls and windows allow sensible heat transfer to or from the space. Infiltration or exfiltration through building components transfers sensible heat as well. Occupants give off sensible heat through respiration and other metabolic functions. All of these sensible heat gains affect the space dry bulb temperature. There are also a number of latent heat contributors within the space. Infiltration or exfiltration through the building exterior walls and windows typically involves moisture transfer as well, and as such affects the space latent heat loads. In addition to being a sensible heat contributor, people add moisture to the space by means of respiration and perspiration. Finally, devices such as coffee makers may add moisture as well as heat via the evaporation of water into the room air. The goal of the HVAC system is accomplished by supplying air at a sufficient flow rate, temperature, and moisture content to offset the space sensible and latent heat loads. Now let's examine some of the psychrometric processes which regularly occur in HVAC applications. The most basic HVAC processes are sensible heating and cooling. These processes add or remove heat from the air without affecting the mixture's absolute moisture content. For example, a sensible cooling process occurs when the air mixture's dry bulb temperature is reduced without reaching the saturation line, thus maintaining its moisture content constant. Conversely, a sensible heating process involves an increase in the mixture's dry bulb temperature with no change in its moisture content. Note, however, that the wet bulb temperature, relative humidity, and enthalpy increase upon a rise in the dry bulb temperature of the mixture. Latent cooling or heating is a process where the mixture's absolute moisture content changes while the dry bulb temperature remains constant. In theory, such a process would be modeled as a vertical line on the psychrometric chart, but in reality would apply to cases where the moist air mixture experiences a phase change, which can only occur outside the ranges of our psychrometric chart. Instead, HVAC latent processes are most often accompanied by a change in dry bulb temperature as well. We'll thus refer to this as a cooling and dehumidifying process where lowering the mixture's dry bulb temperature also results in a reduction in its moisture content. For example, the process of cooling outdoor air from 95-degree dry bulb and 79-degree wet bulb to a temperature of 60 degrees can be illustrated on our psychrometric chart. The air mixture initially undergoes a sensible cooling process until it reaches its saturation line, which is around 74 degrees. Note that the dry bulb, wet bulb, and dew point temperatures are all the same at this point. As the air mixture experiences further cooling, moisture begins to fall out, and any further temperature drop is accompanied by the condensation of additional moisture. This is because the mixture's capacity to hold moisture is reduced as its dry bulb temperature is lowered. Often a diagonal line is used to illustrate this cooling and dehumidification process, but in reality, only sensible cooling occurs until the mixture has reached its dew point temperature. Now let's take a look at a conventional mixing type air handling unit. A predetermined amount of outdoor air is drawn into the unit, filtered, and then passed through an energy recovery device such as a rotary heat wheel. Meanwhile, air returned from the space passes through the opposite side of the wheel. The rotating wheel then transfers heat and moisture between the outdoor airstream and return air that will later be exhausted. The outdoor air is then mixed with return air by means of a damper within the air handling unit. The volume flow rate of the return air passing through the mixing damper is adjusted according to the supply air delivery requirements of the air handling unit. The mixture of outside air and return air is then cooled, and in most cases dehumidified as it passes through a cooling coil. Finally, the blower within the unit discharges the conditioned air mixture into the supply air duct for distribution to the spaces it serves. Now let's look at the individual psychrometric processes that occur within the air handling unit. Our first psychrometric process occurs within the heat recovery wheel. Energy wheels may be designed to transfer sensible heat only, or both sensible and latent heat. First, let's look at a sensible heat recovery wheel. A sensible heat recovery wheel consists of a circular honeycomb matrix of heat-absorbing material which slowly rotates within the supply and exhaust air streams of an air handling system. As outside air passes through one sector of the wheel, exhaust air passes through the other sector. Air streams entering and leaving a sensible wheel are either heated or cooled. No latent heat transfer is accomplished, thus the moisture content of each airstream remains the same. Now let's use the psych chart to illustrate the wheel's sensible heat transfer process. First of all, let's plot our room and outdoor air design conditions on the psych chart. The process can then be depicted as a horizontal line labeled 1. For our example, let's assume the outdoor air leaves the sensible heat wheel at 85 degrees dry bulb. As the humidity ratio remained constant throughout the sensible cooling process, we can now quantify its wet bulb temperature, its enthalpy, and its specific gravity and/or density. Due to conservation of mass, the mass of air passing through the wheel is unchanged. To summarize, the dry bulb temperature and enthalpy of the outside airstream leaving the wheel were reduced, while its humidity ratio remained constant. The density of the outdoor air increased as its dry bulb temperature dropped. Now let's review the process where a total energy wheel is utilized. A total energy wheel's membranes are coated with some type of desiccant like alumina or molecular sieves. These are referred to as hygroscopic chemicals. These coatings have inherent properties that allow them to transfer both sensible heat and moisture from the warmer outside airstream to the return air. Supply air passes through one sector of the wheel, while exhaust air passes through the other side. As the wheel rotates slowly, both heat and moisture is transferred from the warm outdoor airstream to the exhaust air. During winter conditions, these transfers are reversed. This process is depicted on the psychrometric chart as the diagonal line associated with the label 1. The diagonal direction of the process line indicates that both sensible heat and moisture are being removed from the outdoor air as it passes through the rotating wheel. Conditions leaving the wheel now correspond to 84-degree dry bulb and 69-degree wet bulb temperatures. The mass of outside air passing through the wheel is slightly reduced due to the moisture removal. The dry and wet bulb temperatures, humidity ratio, and enthalpy of the outside air are also reduced, while the density of the outdoor airstream is increased. For the remainder of this presentation, we will assume that our energy wheel is a total energy type. The next psychrometric process involves the mixing of the outdoor and return air. After passing through the energy wheel, the outdoor airstream is mixed with return air by means of a mixing damper. The psychrometric properties of the return air differ from those of the outside air, and thus the resultant mixture has its own discrete properties. Due to conservation of mass, the mass flow of the resultant mixture is equal to the sum of the mass flows of the outdoor and return airflow. Other properties of the mixture can be determined by the use of mixing equations that calculate the various psychrometric parameters on the basis of the mass flow airflow rates of the mixing airstreams. The volume flow rate of any airstream is based on its mass flow rate and its density. Determination of mass flow rates are necessary to perform most energy calculations, as both enthalpy and humidity ratios are referenced to mass. This process is depicted on the psychrometric chart as the diagonal line associated with the label 2. Conditions after the mixing occurs are determined to be 80 degrees dry bulb and 66 degrees wet bulb. The mass flow rate of the airstream is increased after mixing and is in fact equal to the sum mass flow rate of the two airstreams. The dry and wet bulb temperatures, humidity ratio, and enthalpy of the mixed air are lower than that of the outdoor air, while the density of the airstream is slightly increased. The next process occurs within the unit's cooling and dehumidification coil. The warm and moist air mixture next passes through a cooling and dehumidifying coil. As it passes, its dry bulb temperature is lowered first to the mixture's dew point temperature. Upon further cooling of the mixture, moisture begins to condense and continues to do so until the mixture reaches its final discharge temperature. The cooled and dried mixture then leaves the coil at essentially saturated conditions. As the mixture passed through the coil, it was first cooled to its saturation or dew point temperature of about 59 degrees. Further cooling within the coil resulted in condensation of moisture from the mixture. The moisture removal process will continue to occur until the mixture reaches its leaving dry bulb temperature. In this case, the cooling and dehumidification results in a saturated mixture at 51 degree dry and wet bulb temperature. The mass flow rate of the airstream is slightly reduced as moisture is removed by the coil. Its volume flow rate is also affected by the change in the mixture's mass flow rate and its airflow density. Our final psychrometric process is sensible heating that occurs as the air mixture is transported to the space it serves. As a conditioned air mixture flows over the blower within the air handling unit, its dry bulb temperature is increased by heat given off from the electric motor driving the blower. In addition, the supply air mixture picks up sensible heat as it passes through ductwork that is located within the warmer return air plenum. These heat gains can result in a 3 to 4 degree rise in the mixture's dry bulb temperature before it is discharged to the space. There is no change in its moisture content, however, as this is a sensible heating process. While the mass flow rate of the moist mixture remains constant, the added sensible heat expands the mixture slightly, which raises its specific volume, thus reducing its density, which results in a slight increase of its volume flow rate. The enthalpy increases as a result of its dry bulb temperature increase, but the mixture's humidity ratio does not change. DOAS air handling units are designed to provide 100% outside air to the space. As such, they do not mix return and outdoor air during normal operation. Instead, the outdoor air leaving the energy wheel passes directly to the cooling and dehumidifying coil without mixing. It then experiences the sensible heat gain that accompanies its final delivery to the space. The psychrometric process involving a DOAS air handling unit are detailed here. As there is no mixing within the unit, the outdoor air mixture leaving the total energy wheel passes directly to the cooling and dehumidifying coil, where it is cooled and moisture is removed as previously described. In most cases, the condition of the mixture leaving the coil is the same as with a mixing type unit. Note that the dew point temperature of the air entering the coil is higher than that achieved by the mixing type air handling unit, resulting in a higher entering air enthalpy, thus requiring more energy per pound mass to condition the air to its off-coil conditions. After leaving the coil, the mixture then experiences the sensible heat gain described as it is delivered to the space. DOAS air handling units are often applied with decoupled space cooling devices such as chill ceilings, chill beams, or variable refrigerant flow systems in order to significantly reduce the required flow rate delivery to the space and thus the cooling energy demand of the air handling unit. DOAS air handling units that are designed to serve spaces with low sensible heat gain ratios, such as classrooms or auditoriums, might be fitted with a secondary dehumidification device, such as a passive desiccant wheel as shown here. A passive desiccant wheel is essentially the same as the total energy wheel we discussed before, except that it is located downstream of the cooling and dehumidifying coil and intended to further lower the moisture content of the air supplied to the space. As the cooled and dehumidified air passes through one sector of the wheel, return air passes through the other. Moisture from the conditioned airstream is absorbed by the desiccant film as it rotates to the return airstream. The lower relative humidity of the warm return air allows the moisture to be transferred from the desiccant to the return airstream. In turn, sensible heat is transferred from the warm return air to the lower temperature conditioned air as the wheel rotates. The psychrometric process in a DOAS air handling unit with a secondary desiccant wheel are detailed on this chart. Conditioned air leaving the cooling and dehumidifying coil enters the desiccant wheel. Moisture from the conditioned airstream is transferred to the return air. In turn, heat transfer from the return air raises the dry bulb temperature of the conditioned air with little change in the total enthalpy of either airstream. Finally, let's take a look at the psychrometric process associated with evaporative cooling. A mechanical direct evaporative cooler uses a fan to draw air through a wetted membrane or pad, which provides a large surface area for the evaporation of water into the dry outdoor airstream. Water is sprayed at the top of the pad so it can drip down into the membrane and continually keep the membrane saturated. Any excess water that drips out from the bottom of the membrane is collected in a pan and recirculated back to the top. The evaporative cooling process lowers the dry bulb temperature of the air as it absorbs moisture while passing through the wetted media. Evaporative cooling is frequently used in dry climates. This map illustrates the areas of the United States where it can effectively be applied. Now, let's review the process within a DOAS air handling unit. Outside air is filtered and passed across the evaporative cooling media, where moisture added to the dry air reduces its dry bulb temperature. The airstream then passes through a cooling and dehumidifying coil, which further lowers both its dry bulb temperature and moisture content before it is distributed to the spaces it serves. Now let's illustrate evaporative cooling on the psych chart. For this example, we choose an outdoor air condition indicative of a hot, dry climate like Phoenix, where sensible design is at 105 degree dry bulb and 68 degree wet bulb. Sensible heat is removed from the outdoor air by the matted absorbent material. At the same time, the warm, dry outside air absorbs moisture, raising the humidity ratio of the airstream. Upon leaving the evaporative cooling media, the outdoor air is cooled to saturation at its intended delivery temperature within the cooling dehumidifying coil. Here are some equations that are commonly used in HVAC calculations. Keep in mind, these equations are all based upon standard air, which has a density of 0.075 pounds mass per cubic foot. As the altitude increases, the density of the air is reduced, and the HVAC equations presented on the previous slide have to be corrected for the change in actual density. This equation allows one to calculate a density correction factor for altitude that can be applied to standard air density, which is 0.075 pounds mass per cubic foot. It can then be applied to correct volume airflow rates to perform the required sensible, latent, and total cooling calculations at the altitude where the system is designed to operate. The altitude correction factor is used to correct equipment performance data for the altitude at which it is planned to operate. As you can see, the altitude correction factor is significant in high altitude locations like Denver, Colorado, whose altitude is 5,285 feet, or Tucson, Arizona, at 2,549 feet altitude. For lower altitudes like Atlanta, Georgia, or coastal areas like Los Angeles, correction for altitude is not so important.